The last lecture we were examining the phenomenon of dispersion. To recall, diffusion is the transport of mass, momentum or energy due to the molecular fluctuating velocities. Convection is the transport of mass, momentum or energy due to the fluid velocities. There are situations such as turbulent flows or flow in a packed column that we shall see a little later, where the fluid velocities are rapidly fluctuating functions of either position or time. A turbulent flow is an example, where after the transition to turbulence, the fluid velocity profile in a turbulent flow at a given location is a rapidly fluctuating function of time. It contains an average component, of course, but there are rapid fluctuations about the average. And so we were examining that in the last lecture. The fluid velocity at one particular location, okay, shows a fluctuation with respect to time in all three components. There is an average velocity in the streamwise flow direction, but there are fluctuations about the average. The average in this case is defined as a time average, okay, 1 over the averaging time times an integral from 0 to the averaging time of the velocity with respect to time. This averaging time has to be large compared to the time for variations, time scale for variations in the fluctuating velocity. Okay, that is how you define a time average for a flow that is statistically steady on average. And then we define the fluctuations about the average, okay, the fluctuations about the average in the three different directions. In a flow where there are variations in the concentration or temperature with respect to time, there will also be fluctuations in the concentration and the temperature fields. Okay. So, therefore, we can define the concentration or temperature as the sum of an average value. Note that this is a time average at a location, okay. The sum of an average value plus a fluctuating component. And then we took the definition of the mass flux, okay. The mass flux, which is just the product of the normal velocity times the mass density or the concentration at that location. And then we integrated this mass flux with respect to time. It is the product of the velocity and concentration. The velocity is the sum of an average plus a fluctuation. The concentration is the sum of an average plus a fluctuation. And when you expand it out and do a time integral, you get one part here, okay, which is the mean velocity times the mean concentration. Okay. This should be the mean concentration here. The mean velocity times the mean concentration, which is the convection due to the mean flow, okay, the mean velocity times the mean concentration. And then you get this second component here, which is the time average of the product of the fluctuations. Okay. Note that the time average of the fluctuating velocity is 0, the time average of the fluctuating concentration is 0. The product of the two does not necessarily have to be 0, okay, especially when they are correlated. The correlations between the velocity perpendicular to the surface and the mass density at that point gives you a flux, which we had referred to as the Reynolds flux. Okay. This is due to the fluid velocity fluctuations. This is an additional convective flux in addition to the flux due to the mean flow, okay, and that is why it's the flux due to the fluctuating velocities. It is called the Reynolds flux, where, for example, the average of Vx prime C prime average is equal to 1 over TAV integral 0 to TAV dt times Vx prime of t C prime of t. Vx prime and C prime are individually averaged to 0, but the product does not average to 0. Similarly, we have a Reynolds flux for heat and the Reynolds stress for momentum. Note that the Reynolds stress for momentum has a negative sign because it is defined as the force exerted on the surface below, okay, on the volume below the surface. And I had given you a concrete example of how you could have a non-zero value for the Reynolds flux even though the velocity and the concentration both are 0. We had considered this case where concentration had a particular frequency, velocity had the same frequency but with a phase shift, and we saw that when you take the product and then calculate the average, you do get something that is non-zero even though the velocity and the concentration themselves are both equal to 0. Okay. And how do we calculate this Reynolds stress or Reynolds flux? Okay. Of course, if we solved the fluid velocity equations exactly, we would know the velocity field as a function of position and time, and from that we could calculate these fluxes. Okay. But of course, usually in a turbulent flow it is difficult to compute the exact velocity field, and you may also not be interested in all of the details of the fluctuating velocities. What you want to know is what is the actual flux or the stress, and you cannot just calculate the stress based upon the mean velocity and the mean concentration, because in a turbulent flow the dominant contribution to the flux, as we will see, is due to fluctuations. So, in that case there are models for the stress and the flux which are similar to the models for diffusion due to molecular motion. Okay. These are called the mixing length models. Okay. So, the Reynolds stress, okay, let us say the heat flux, the Reynolds flux in some particular direction, okay, is the average flux in that direction, is equal to rho Cp into the average of the velocity fluctuations times the concentration fluctuations, where this is the time average. Okay. The Reynolds mass flux is equal to the concentration times the component of the velocity fluctuations. Note that the flux has a direction, it is the same direction as the fluid velocity, because it is the velocity perpendicular to the surface that contributes to the flux across the surface. Okay. And similarly, the Reynolds flux minus rho Vx prime Vz prime. Okay. Here I am assuming that the density is a constant. Okay. Now, these are modeled by relations that look similar to the laws that we have for molecular diffusion. Okay. The model for the Reynolds flux, for example, is this is equal to minus a Reynolds diffusivity times dC bar by dZ, okay, where C bar is the average concentration. Okay. So, to put it in perspective, okay, if I have some field here, okay, if I have some field here in which I have some turbulent flow, okay, with turbulent eddies in all directions, okay, and if I want to calculate the Reynolds flux across the surface, this model basically tells you that you do not need to know what is the actual fluctuating concentration at that surface, okay, as a function of the z. What you only need to know is the average concentration. Okay. The Reynolds flux is related to the gradient in the average concentration. Note that the average concentration was defined as a time average. That time average is in general a function of position. Okay. So, if I take the gradient of this average concentration, multiply that by a diffusion coefficient, I will get the Reynolds flux. This is called the mixing length model. Okay. Similarly, for the heat flux, okay, the model is that Qz Reynolds, okay, is equal to minus alpha r. I see. Okay. Where alpha r is the diffusivity, the turbulent diffusivity. Similarly, the shear stress is equal to the turbulent viscosity, okay, or the turbulent, it is called the eddy viscosity, okay, where the so let me just write it in terms of a diffusion coefficient for simplicity. I will write this as the density times the kinematic viscosity or the eddy diffusivity. Okay. In this case, alpha r, dr and nu r are all diffusion coefficients. They have dimensions of length square per time. Okay. These are called the turbulent diffusivities. In analogy with the molecular diffusivities for a molecular system. Okay. They should strictly be speaking be called as dispersivities, but traditionally they are labeled as diffusivities. Okay. And the mixing length model for this basically says that all of these are equal to some constant. Okay. Okay, times a characteristic velocity times a characteristic length. Okay. Okay, this so these dispersivities or the diffusivities have dimensions of length square per time. They are modeled as a characteristic velocity times a characteristic length. The characteristic velocity is the characteristic velocity of the fluid velocity fluctuations, the magnitude of the fluid velocity fluctuations in the cross stream direction, and the characteristic length. Okay, okay, it's a characteristic fluid velocity fluctuation. It should not be Vx prime, it should just be P prime. And this characteristic length is what is called the mixing length. Okay. In analogy with the molecular velocity of fluctuations and the mean free path or the microscopic scale. Okay. So, that is the analogy here, that it can be expressed as a characteristic velocity times a characteristic length. In which case all of these are directly proportional to each other, that because the mechanism of transport is the fluid velocity fluctuations, whether it is mass, momentum or energy, the diffusivities will all be of the same order of magnitude. They will scale as a characteristic velocity times a characteristic length. Okay. Now, this analogy is sort of similar to what we have for molecular diffusion. Okay. So, in the case of molecular diffusion as well, right, the molecules that were coming from that were crossing a surface, if you have a surface here, the molecules that were crossing a surface were coming from some distance above the surface, okay, where the concentration was different if there is a variation in the concentration. Okay. So, the molecules crossing a surface come from some distance above that surface, those going from above to below, and molecules going from below to above come from some distance below the surface. Okay. And the concentration was different at these two locations. So, the flux was related to the velocity perpendicular to the surface, which is proportional to the root mean square velocity, and the concentration at locations above and below the surface. They vary from the concentration at the surface by a value mean free path times the concentration gradient. Okay. In the mixing length models, the rationale is the same. Okay. Rather than having molecules crossing a surface, you have correlated parcels of fluid in motion, okay, called eddies, okay, which cross the surface. Okay. And the idea is that the fluid that is crossing the surface from above comes at some distance above the surface, a distance comparable to this mixing length, okay, coming from above to below. Fluid going from below to above comes from below the surface by a distance comparable to this mixing length. Okay. This mixing length roughly gives you the distance over which a correlated parcel of fluid transports, okay, mass, momentum or energy across a surface. Okay. And the velocity is the velocity of these fluid velocity fluctuations. And therefore, the diffusivities are proportional to the product of the velocity, fluctuation and this mixing length. Okay, that is the rationale. It turns out this is not as well grounded an explanation as it is for the molecular case. In the molecular case, we know that the mean free path or the microscopic scale is much smaller than the system size in most macroscopic systems. Therefore, if you recall, we had expanded the concentration at a location in a Taylor series expansion and retained only the first term in that expansion, because the higher order terms were multiplied by higher powers of the ratio of the mean free path and the macroscopic scale. In the case of turbulent dispersion, it turns out that the length scale of the largest eddies, length scale of largest eddies are comparable to the system size. Okay. The length scale of the largest eddies in a pipe flow, for example, are comparable to the system size, and therefore, you cannot truncate the Taylor series expansion at the first term. The ratio of the characteristic size of the eddies to the system size is not a small number, in general, and therefore, you cannot truncate the series at the first term. And because of that, the Taylor series expansion that was used for getting the Fick's law, Fourier's law and Newton's law is not valid in this case. And because of this, this is not an exact model. This is not as firmly does not have as firm a foundation as the molecular diffusivity. This has to be considered an approximate model. The diffusivities are not fluid properties. The turbulent diffusivities are not fluid properties, they are flow properties, because that is transport due to flow. Whereas in the case of diffusion, those were fluid properties, they depend only upon the temperature and the mean free path. In this case, they depend upon the details of the turbulent flow, and therefore, this mixing length and the velocity are parameters which are flow specific. They have to be calculated for each different configuration that you are analyzing, whereas the diffusion coefficients, molecular diffusion coefficients, are material properties. They are the same regardless of what the flow configuration is. So, these have to be considered as models which have to be fitted to actual flow configurations rather than as material properties. So, these are flow properties because the mechanism here basically is convection. However, this transport is actually much faster in comparison to the molecular diffusion. So, for example, for a typical flow, let us say you had a velocity of about a meter per second, or even 0.1 meters per second in a tube that was of diameter a centimeter or so. So, we have V prime. Even if we take a low velocity of 1 centimeter per second, you get 0.01 meter per second as the velocity. The mixing length is the macroscopic length. For a pipe of diameter 1 centimeter, this will be 0.01 meters per second. And therefore, the diffusivities, the 10⁻⁻⁴ meters square per second. Even for this low velocity of a centimeter per second in a tube of diameter 1 centimeter. Contrast this with 10⁻⁵ meters per second that we had got for diffusion coefficients in gases, and in liquids it can go down to 10⁻⁹ for small molecules mass diffusion. There is a range. So, these turbulent diffusivities are usually much higher than molecular diffusivities in flows where turbulence is important. And in those cases, the primary mechanism of transport is due to turbulent diffusion. but because the largest scales are comparable to the system size, it is not possible to compute this exactly for a material. You have to compute it depending upon the configuration. Okay. For the flow configuration, these have to be estimated, okay, based upon the flow characteristic velocities and the characteristic length scales. Okay. So, to summarize, in turbulent flows there is a time variation in the quantities: mass, momentum, concentration, velocity and temperature. And the correlation between fluctuations in velocity and the temperature or concentration result in fluxes of mass or heat, and these are related to the time averages. The simplest model is the mixing length model, very similar to that for molecular diffusion coefficients. And however, this mixing length model is a model. It is not exact, because it makes assumption that we can relate the fluxes to the first derivative of the concentration, temperature or velocity fields. That is not a good approximation for turbulent flows, because the largest structures in turbulence are comparable to the system size, and therefore, if you try to expand properties locally, the series does not converge, because the expansion parameter is the ratio of the flows, the mixing length and the system size, which is not small in general turbulent flows. So, that is as far as turbulent diffusion is concerned. Okay. Let us examine two more examples. One is diffusion in a packed column. Okay. We had seen an example of this when we looked at correlations. Okay. A packed column consists of particles, okay, which are closely packed, and the fluid flows in the gaps between these particles. Okay. Okay. So, the fluid follows tortuous paths between the particles. Okay. Okay. And because of that, there is an increase in the contact between the fluid and the particles, which can enhance many transport processes. Okay. In this case, the fluid velocity is a rapidly fluctuating function of position. Okay. Depending upon whether a particle is obstructing the flow or not, the fluid velocity has to go around the particle. So, if you look at the particle scale, the fluid velocity is a rapidly fluctuating function of position, even though at steady state it may not vary with time. Okay. However, if I define the velocity field over a characteristic volume larger than the particle, and I average the velocity over the entire velocity field, then I will get a velocity that is only in one particular direction. Okay. And that velocity is going to be equal to the superficial velocity divided by epsilon, where I had told you that the superficial velocity is the velocity through the, which is the flow rate divided by the cross sectional area of the bed without particles. Okay. And epsilon is the porosity. Okay. So, now if I separate out the velocity into a spatially averaged part, which is all in the same vertical direction and uniform on average, and a fluctuating part which basically takes into account the change in direction of the fluid velocity as it goes through the particles. Okay. The transport due to this fluctuating part, the spatially fluctuating part, is what is called diffusion in a packed column. Okay. So, if I separate out this tortuous velocity into an average velocity, okay, which is just equal to the ratio of the velocity divided by the porosity. Okay. If I just take it as the ratio of the superficial velocity by porosity, and then I divide define the fluctuating part as the actual value of the velocity. For example, here the velocity is in this direction, whereas the average velocity is still in this direction. So, the difference between those two will be the fluctuating part. Okay. Then the transport due to this fluctuating part is what is called dispersion in a packed column. Okay. And that dispersion in a packed column can be estimated quite easily. Okay. For example, if I consider the flow in a packed column, okay, a fluid element that is coming here, okay, you consider two nearby fluid elements that are coming here, coming upwards. One of these will travel around the particle on the right and the other will travel around the particle on the left. Okay. So, therefore, the distance between two nearby points, okay, increases by approximately a particle diameter, right, as the as the fluid element crosses one particle diameter. Okay. So, the time taken for the volume element to cross one particle diameter, note that the velocity is equal to Vs by epsilon. Okay. Okay, will be equal to the particle diameter divided by Vs by epsilon. Okay, that is the time taken to cross one volume element. The horizontal distance traveled within that time, okay, is approximately one particle diameter, because a fluid, two nearby elements are separated by a diameter when they cross one particle. Okay. And therefore, the dispersion coefficient will be equal to the square of the distance. Note that the dispersion coefficient has dimensions of length square per time. Is going to be equal to the square of the distance that is traveled in the horizontal direction, okay, the mean square of the distance divided by time, okay, divided by d by Vs by epsilon. Okay. So, this you will see will be Vs by epsilon into d. Okay. That is the characteristic velocity with which the flow is passing through the pores times the diameter of a particle. That is going to be equal to the dispersion coefficient, okay, for the flow through porous media. And this dispersion coefficient will be the same for mass and energy, okay, because as a fluid element comes in and it has to go around a particle, the spread of that fluid element is approximately one particle diameter when it crosses a distance comparable to a particle diameter. Okay. And because of that, there is going to be a dispersion which is proportional to the particle diameter times the velocity through the pores. We will see this in further detail, do a more careful calculation for structured porous packed beds a little later in the course. Okay. The other kind of dispersion that we encounter is what is called axial dispersion in a pipe, or a Taylor dispersion. Okay. Okay, so let us compare two cases. One is where we have a plug flow, okay, where the velocity is a constant everywhere, okay, and the other is where we have a parabolic profile. Okay, the plug flow is of course not physically realistic, but we will just use it for the purpose of understanding what is the Taylor dispersion. So, if I insert a plug of material here, it is going to get convected due to the mean flow, okay, and it will diffuse, okay, because of diffusion, and it will slowly spread, okay, as it goes downstream because of molecular diffusion. Okay. So, if I have a plug which was well confined here, at some later location it will expand a little bit, and at still some later location the expansion will be more. Okay. What happens if I have the same plug in a parabolic flow? Okay. If I introduce a plug over here across, okay, after some time it will expand, but it will also, okay, it will also be stretched by the flow, okay, It will also be stretched by the flow after some time, because the fluid velocity close to the wall is 0. So, there it does not move. At the center it is a maximum, and therefore, you have a maximum displacement at the center. So, at some later time you will get something like this, and at a still later time you will get something like this. Okay. And then there is diffusion around this. Okay. There is molecular diffusion around this, and because of that the axial spreading of this element, this plug element here, okay, of material that has been introduced or energy that has been introduced, is much faster in a laminar flow in comparison to molecular diffusion. Okay. And this is the phenomenon that is called Taylor dispersion. Okay. And this dispersion coefficient, okay, the dispersion coefficient for Taylor dispersion actually has an unusual dependence on the molecular diffusivity. Okay. For the flow in a pipe you can actually calculate this. We will see this a little later. You can show that this is equal to times the molecular, this is the Taylor dispersion. Okay, so the Taylor dispersion coefficient, okay, is equal to V square d square, V average velocity square times the diameter square. Okay. This is the diameter and this is the flow velocity. The average of this is the average velocity. V square times the average velocity square times the diameter square divided by 192 divided by the molecular diffusion coefficient. So, this actually predicts that the dispersion coefficient is inversely proportional to the molecular diffusion coefficient. The reason is because when the diffusion coefficient is larger, right, this plug will immediately spread. Okay. If the diffusion coefficient is large, this plug will immediately spread before it convects very far. Okay. If the diffusion coefficient is large, the plug will spread before it convects very far. Okay. If it is small, then it will get deformed in this way. It will not spread because of molecular diffusion. It will get deformed and it will spread over a larger distance, from where molecular diffusion tends to equalize the concentration across the pipe. Okay. So, it stretches a longer distance before molecular diffusion transport it across the pipe, and because of that the dispersion coefficient for a plug is actually much higher than the diffusion coefficient, the molecular diffusion coefficient, when the Peclet number is large. Okay. So, this is for when the Peclet number is large, the dispersion coefficient is actually much higher than the molecular diffusion coefficient. It is proportional to the inverse of the molecular diffusion coefficient. So, the diffusion coefficient is less, the dispersion coefficient is more. Okay. It is proportional to V square times d square. You can verify that it has dimensions of length square per time. Okay. So, this is a brief summary of dispersion. Okay. Dispersion due to fluctuations in time in a turbulent flow, due to fluctuations in space for the flow around a packed bed, and the dispersion because the stretching of elements of mass or heat that are introduced due to the laminar flow in the case of Taylor dispersion. Okay. So, with this we complete our discussion of diffusion and dispersion. Next time I will start unidirectional transport. I will see you in the next lecture.